All right, guys. So we're going to walk through this. Now, we want to know when holes exist. So holes exist when the denominator, or I'm sorry, when the canceled factors, okay, make the denominator equal 0. When the canceled factors make the denominator equal to 0. So walking through this particular problem, the first thing we're always going to want to do is simplify. And I heard someone say factor. Factoring is how we're going to simplify it. So if we take a look at our first expression here, okay, well, this first one, we can factor a 5 out. That's right, Andrew. Thank you for your enthusiasm. Oh, you're right. Okay, so we get x plus 4. And on the bottom, we can factor that out to x plus 4 times x minus 3. Now, we look to see if there's anything we can cancel. We're going to go ahead and cancel the x plus 4s. And that's going to leave us with 5 over x minus 3. Okay? Now, we don't want to forget about that x plus 4 because when x plus 4 equals 0, we end up with a 0 in the denominator. That is going to create a hole. I'm going to go ahead and jump forward here. X plus 4 equals 0, or when x is equal to -4, that is a hole. And we're going to want to remember that. Yes, Andrew?
So whatever cancels out the hole?
As long as it would at some point make the denominator 0. So, for example, if you canceled like a 2, or you canceled this 5 with something on the bottom, that wouldn't make the denominator 0. Okay? Now, vertical asymptote. Yes?
For the holes, does it have to be a coordinate?
Wherever the graph is at x equals 4, there will be a hole. So I'll show it to you in a sec. Okay? All right. Now, vertical asymptote. Okay? The vertical asymptote is simply when our simplified expression has a denominator of 0. So we look at our simplified expression, and it'll have a denominator of 0 when x minus 3 is equal to 0, or when x is equal to positive 3.
Are you sure?
Positive. Now, when we're looking at the horizontal asymptote, remember, we're trying to predict what will happen when x gets really big or when x gets really small. Now, if we look at the expression here, okay, one, we could look at our actual rules and just kind of memorize it. But if we want to go ahead and take a step further, we can say, well, we want to know what happens. Well, when 5 is just going to stay the same, and the bottom will actually approach infinity. So we end up with, right, we have x minus 3. If we put something really big, like a bajillion thousand, okay? Well, we're going to have a really big number on the bottom. The bottom's going to get bigger and bigger and bigger and bigger. The top isn't. Well, if we have 5 over a really, really, really big number, the bigger that bottom number gets, the closer it's going to get to 0. So y equals 0 is our horizontal asymptote. If it gets really small, okay, well, then we're going to have 5 over a really big negative number. It'll still approach 0, right? You don't have to really look at both, but both will behave the same way. Now, if we want to find the x-intercept, what are we going to do? What do we want to know when? Y equals 0, and the whole thing will equal 0 when the numerator equals 0. Well, when is, so if we do 0 is equal to 5 over x minus 3, okay, if you don't want to memorize the whole numerator thing, if we just set up this equation, well, can I do this? Put that over 1?
Yes.
And then we cross multiply, and we get 5 is equal to x minus 3. Oh, wrong way. Sorry.
What?
5 is equal to 0. 1 times 5 is 5. 0 times x minus 3 is 0. Well, when's 5 equal to 0?
Never.
Never. That means there's no x-intercepts. Because the graph never crosses the x-axis.
Oh, yeah.
Okay? Now, looking at the y-intercept. Well, when we're on the y-axis, what's always true? X equals 0. So we set x equal to 0. And here's what's nice about using a simplified expression. We want to know what f of 0 is. Well, if I look at my expression, it's just 5 over x, or 0 in this case, minus 3. So our our y-intercept will happen at 5 over negative 3. Well, since we're going to be graphing this, I'm going to go ahead and make that 1, or negative 1, over 2/3. This is an example where mixed numbers are actually kind of nice. Right? Now, let's go ahead and graph it. I'm going to use a different color to illustrate the vertical asymptote. But if we start, it's at x equals 3. So we go over 3 spots. 1, 2, 3. We're right here. Now you generally want to use a dashed line to show that it's not actually part of the graph, okay, but it's just a boundary. Remember, this is like one of our fences. Now, we want to do the horizontal asymptote. I'm going to go ahead and use, again, I'm going to use a different color. And our horizontal asymptote is at y equals 0. So we're going to go here to y equals 0. Make another dashed line. Remember, this barrier only is going to really work completely anyway when we are at the ends of the graph. The farther we get out, the more likely it is that it will start approaching that line. Now, moving on to the next piece. Okay, well, we're going to have to remember that when we finally do graph it, we need to create a hole at negative 4. I'll get to that in a moment, though, because we haven't graphed anything yet. Our x-intercept, well, we know our x-intercept is, there aren't any, and our y-intercept is at negative 1 2/3, right here. Now, looking at this, do we really have a very good idea of what our curve is going to look like? No. So we need to plot additional points. Now, the points you should choose, okay, well, I want to know how it behaves to the left of our vertical asymptote. Because that asymptote, remember, is kind of like a magnet or reverse magnet. It's going to push your graph away from it. So if we want to know how it relates next to this, why don't we see what happens when x is equal to 2, right next to it. So I'd like this section of the classroom here to find f of 2. You can use the simplified expression. It should be pretty quick. Okay? Then we also want to see maybe what happens to the left of our y-intercept. So let's also do f of negative 2. Now, I want to see what it does to the right of our vertical asymptote. So let's see what it does right here at f of 4. So this section of the classroom here, go ahead and find f of negative 2. The next section over there, f of 4. And then let's go a little bit farther and see what happens at f of 6. Okay? And that can be what the very right of the classroom can do. All right, so the left side here, what is f of 2? Yeah, we're going to have 2 minus 3. 5 divided by negative 1 is negative 5. F of negative 2, what was it?
Negative 1.
We get negative 1. And f of 4, what is that?
5.
And f of 6? 5 over 3. Oh, sorry. There we go. Okay? So all you're doing here is plugging the input into our simplified expression. That'll give you an output. So I know that when x is 2, y is going to be negative 5. So I come over to 2, and I go down to negative 5. I know when x is negative 2, y is equal to negative 1. So I go over to negative 2, and I know my graph is right here. When x is 4, f of 4 is 5, so I'm going to be right up here. And when when x is 6, I'm at 5/3, which is the same as 1 2/3. So I'm right up at about here. Now, once you get more comfortable with this, you might want to plot another point or two if you aren't familiar with this type of graph. I'm a little more familiar with it. I know that my graph is going to be something to the effect of this. Now, as our graph approaches negative infinity, it'll get really close to 0, but it'll never get there. Up here, it gets really close to our vertical asymptote, then it kind of pushes away, and then it gets really close to 0, but it's never quite going to get there. Now, there's one thing that I forgot. At x equals -4, my graph does not exist. So I'm going to go over to -4, 1, 2, 3, 4, and I'm going to put a hole there. Okay? Now we have graphed our graph. We've planted our house. Okay? You can try the next one. The homework should be similar to this. We'll work more on this later on Monday.
This is right for the second.
Mm-hmm.